Hello, good afternoon. I hope all you are fine. And let's check out what we have done in the last previous course. In the previous course, we have studied power and torque equations of round rotor synchronous machine. We have derived some equations defining torque and power. And here it is, power and torque in round rotor synchronous machine. In fact, that equation is valid for round rotor or cylindrical rotor machine. Sometimes it is also called as smooth air gap machine or turbo alternator turbo machine. All those have the same meaning. I think you remember that is the final equation for one phase. For three phase, let's write down here. That's valid for one phase. For three phase, total output power is equal to 3 times voltage EMF over excess times sine delta. That is the total power induced in synchronous machine. Sometimes we say converted power, induced power. That is the power induced in that is the electric power induced in generator, or that is the mechanical power induced in motor application. That is the converted power. And here you see these term can be defined as maximum value, because you see the argument is a function of sine, so power is varied by sine, and we have already defined some regions. Delta must be less than pi over 2 and must be greater than minus pi over 2. And that was somewhere here. Let me find it in Turkish edition. That is the power or torque function. Here you see that is the torque function for three phase. Armature power, we said armature power. In Turkish we call döner alan gücü, endüklenen güç, moment, TA, armature power, armature torque right now. It is just equal to induced power over angular speed of the shaft. That is the new parameter coming down here. So let me write first of all PA, which is 3 times voltage EMF over XS times sine delta, and now here is WS, that is the shaft speed or synchronous speed, the same, coming from 2 pi ns over 60, and ns, you know, it is coming from frequency at 60 f over pole pair number. So generally this guy and this guy and this guy is constant, so power can be altered mainly this term, sine delta. For example, here's a generator. You apply some mechanical power and then you convert it into electric power. Converted power is this 3 voltage EF over excess sine delta. That is the converted power inside the machine, somewhere here. And then here is some mechanical losses in terms of frictional and windage losses. And here are some copper losses in armature. And then this guy convert mechanical power into electric power. But take care. Mechanical power in mechanical world, as you see, that is the torque. Mechanical world, power is equal to mechanical torque times mechanical speed of the shaft, which is equal to synchronous speed. And as you see, under constant frequency, synchronous speed is constant. Otherwise, your machine cannot deliver electric power or mechanical power. Synchronous machine only converts energy at synchronous speed. Otherwise, machine will be out of synchronization. There is no stable operation. For example, if you calculate NS is under the let's say 60, Turkish frequency 50, and Popper number, let's say it is 1 here, 60 times 50 over 1 makes 3000 RPM. And now this guy cannot be operated neither 3001 RPM nor 2991 RPM. It is impossible due to the constant frequency. Of course, the machine can be operated those RPMs, but it must be coming from the frequency. For example, frequency would be 49.8 or 50.05. Those kind of different frequencies may result in different speeds, so machine only can deliver power on these speeds, otherwise cannot convert energy. Otherwise machine will be out of synchronization, machine will be in a unstable region. If you exceed 90 degrees in positive or minus for delta, which is low angle, there is no stable operation here and here. Okay, now today those were the topics we have studied in the previous course. Today's topic, I will extend efficiency a little bit today. In fact, you are ready for efficiency because we have we know output power. For example, if this is generator right now, power flow is this. We are already familiar with power flow, and then that is the main power route. Mechanical power will come and convert it into electric and then supply, let's say here's grid or loads, that mechanical power supply the national grid. That is the main power arteria. And then you know what the efficiency is. Efficiency is always output power over input power. Now that is the efficiency. If you multiply it by 100%, so you can express efficiency as percentage. Generally we express efficiency in percentage. Let's talk about the generator. Let's talk about generator operation. In generator operation, we apply some mechanical input power. First of all, here's the device, synchronous generator, having 3-phase, star connected. Let's say here are 3 electrical armature terminals, and then let me say here's the shaft, and you apply some mechanical power, you convert it into electric power, and then to make energy conversion you need some magnetic field, because your device converting electric energy, mechanical energy into electrical energy by using electromagnetic medium. So here we apply some field current, DC current to rotor, main field coil, and then here will be some magnetic field produced in the rotor. When you rotate rotor, that magnetic field rotates around the stator slots and then induce electromotive force in 3-phase. If you have a properly arranged 3-phase winding in armature. Then let's go further. Applied mechanical power will be some portion, a little portion will be dissipated as heat. Here let me say mechanical losses, let's say frictional and windage aerodynamic losses, we call PS plus V in Turkish, sürtünme artı vantilasyon. And then after losing or dissipating a little bit in terms of mechanical losses, rest of the power will be converted into electric power in the armature. That power in the armature, here's the equivalent circuit, plus here's the excess, here is the PPP resistance, armature winding resistance belonging one phase, and here is the one phase terminals of the armature winding. The induced EMF is here. Armature power will be induced on these element. Energy conversion occurs on this element, and it is in terms of EF, that is the current for generator, outgoing current, and then the angle between those two phasors. But here those are only magnitude in terms of RMS values. Here is cosine psi, that is the angle between EF and I1 phasors, from EF to I1. Okay, that is for one phase, but for 3-phase power you should multiply that equation by 3. Do not forget. And then power is induced here, that device, 3 times EF times I1 times cosine psi, and then some portion will be lost here on this element, which is copper losses in armature. It can be written as 3 times again for 3-phase I1 squared times Ra. There is no active loss on this element, so resultant power will be delivered to network or load. It is equal to 3 times again one phase terminal voltage, which is V1, one phase terminal current, and then cosine phi, which is power factor. We call power factor. You know, phi is the angle between V1 phasor, which is generally chosen as reference, and I1. That is the phase displacement or power angle. And now someone can ask whether there are some iron losses or not. In case it is given, iron losses or core losses are here. It acts as if mechanical losses, as if it is a kind of mechanical losses. So it is generally given in mechanical losses, so I never mention about this, so I clean core loss here, but you should know it is somewhere here. Okay, and then core loss, it can be Foucault losses or eddy current losses and hysteresis losses. Okay, now gentlemen and ladies, we can calculate efficiency. Efficiency is by only referring these chart, output power, which is P here, and input power, which is mechanical power. Let me say electrical, okay, electrical output over mechanical input. Or someone can say, say those are power losses, total power losses, total power losses. Some are mechanical, some are electrical, total losses. So if you consider like this, applied input power, some of the power will be dissipated in losses, total losses. Rest of the power will be on the electrical terminal. So if you cut here, or if you write Kirchhoff's node equation for this node, input power or mechanical power can be said that it is equal to electrical power plus total losses. Okay, let me write it down again. Efficiency, electrical output over instead of mechanical power, you substitute the equivalent, electrical plus total losses. Total losses. That is the equation. That is the efficiency equation. You can simply multiply by 100 and express result as a percentage. It is always on the desk. It is easy to find out the parameters and calculate the efficiency. There's something more to say. For example, here we only deal with stator armature coils, but ladies and gentlemen, in fact here's a field winding resistance, and here would be some copper losses on field coil. It can be simply written as IF squared times RF. Here's DC. There is only one winding, so there is no need to multiply it by 3. There is no 3-phase. It is DC. In case it is given, in case this element is given, and in case overall efficiency is asked, It can be summarized like this: electrical output over electrical output plus total losses. What are they? P mechanical, sürtünme artı ventilasyon, mechanical losses, plus if there is any given core losses, here it would be, if there is armature resistance given, here you see armature resistance, there is copper loss in armature. In case field resistance is given, so here will be copper loss in field coil. As you see, those are called as total losses. Total loss. Sometimes we say if we add this guy, we call overall, including stator and rotor losses, overall efficiency. But in fact, if it is given here, you should add field current losses, copper losses here, and that is the efficiency. Whether you say overall or not, that is the efficiency, including rotor losses, rotor copper losses. Now, it is the same. We started for generator operation, but that is the main energy artery. Think about motor operation. So here you see that was the main energy corridor or artery. Here is the mechanical side, here is the electrical side. Just in the mid, just in the mid, there is armature or converted power. Somewhere here, copper loss in armature. Somewhere here, mechanical losses. So, in terms of sürtünme ve ventilasyon, friction and vintage. Okay, now take care. I'm just changing the main energy direction. You apply electric power, you convert electric power into mechanical power. After losing some losses, here's the resultant mechanical or net mechanical output in terms of torque and angular speed of the shaft. That is the chart and relation or power balance of synchronous machine in motor operation. In the previous page we have studied on generator operation. Again, efficiency is the same. Mechanical output, blah 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 blah. Right now, output, take care, output over input. Let me correct it. Output power over input power. Now, gentlemen and ladies, output is mechanical and the input is output plus total losses, which are mechanical, sürtünme artı ventilasyon. If there is some core losses given, yes, it would be here, plus copper loss in armature, yes, if array is not neglected, Generally we neglect it, but in case it is given, you should calculate copper loss in armature. Again, we generally neglect rotor losses. We generally not deal with RF, but in case it is given, so copper losses perhaps can be calculated and must be added here to calculate total losses. That is the efficiency equation for motor operation. That was the missing topic. In fact, we talk about the power balance of machine. That is the power balance. We don't need to write down stray losses. In the previous week we have discussed stray losses, what they are. Stray losses are generally occur in overloaded cases, underloaded and overloaded cases. For example, you can calculate windage, friction, core losses, blah blah. You can calculate all the losses, but the equation is something will be missed. So there will be some additional losses out of those. Generally they are due to magnetic field origin losses, but due to under heavy armature reaction, some magnetic field lines change their route and cause some additional losses. Those kind of losses would be called as stray losses, but we never deal with undergraduate courses. Okay, it is quite a small amount of losses, stray losses under heavy loaded cases. Okay, we have already know some about power balance, but today we have especially focus on efficiency and overall efficiency. Okay, and then today here is the power. Now in the previous course we have calculated induced power by neglecting array. We have used a phasor diagram to make some substitution, because such an equation cannot give any information about stability. If you write power equation in terms of delta, theta, right now you can talk about stability. Here you see, if you draw such a formula, if you draw a graph for such an equation, you observe that power will be increased and then decreased. So that is the maximum power. And then take care, gentlemen and ladies, this point is very important. For generator operation, I said mechanical speed is constant due to constant network frequency, and I said machine under constant frequency cannot be operated in a different speed. It is impossible to operate machine in a stable region. If the speed is different than synchronous speed, you should know that machine is out of stability. Okay, now that guy is constant. To increase applied input power, we increase applied torque. torque times angular speed, which is constant, makes mechanical input power. So we change applied input power, we adjust it by only using torque. There is no speed change. But, ladies and gentlemen, remember the operating principle of synchronous machine or generator operation. In generator operation, here is the stator, here is the stator, and then here are three-phase terminals. When you generate, here, let me say, here is a rotor. Just imagine here's a simple magnet rotating, and then that magnetic field rotates at a certain speed, and then that magnetic field coming from M pole cuts armature coils somewhere here located in stator slots, and then there are some three-phase AC winding. It induces three-phase power, electric EMF first, and then when there is a load, let me say here is the grid, when there is a grid connection between machine and grid connection, and then here will be some electrical delivery, electrical power exchange. You apply some mechanical input power, that guy will convert it into electric power and then supply grid. In case here are three-phase currents flowing in three-phase AC winding, here is a rotating magnetic field at the speed of ns will appear, and then they are locked each other. Let me say that is S and that is N, because those magnetic fields must be locked, synchronized, because remember Newtonian equation, F is equal to ma, that means total F acting on a mass will be equal to mass times acceleration, and then torque is equal to J alpha. J is the inertia of the rotating body, and torque is the total torque acting on inertia, that is the angular acceleration, which is the time derivative of angular speed. Now, under steady state operation, dw over dt is 0 because speed is constant under stable operation. Okay, if this is a constant, right hand side of the equation will be 0. There is no speed change because acceleration is 0. J, remember, any solid rotor having a radius r and mass of m rotating in such an axis, inertia can be calculated as 1/2 mr squared. So here you see m is always positive, r squared is positive, so j is always positive. Now this guy is 0 and right hand side of the equation is 0 and left hand side is total torque. It is acting torque minus, let me say, acting and reacting. And what does it mean? Acting, this guy is a generator, that is the torque coming from prime mover Here's a turbine, for example, called as prime mover, ana tahrik makinesi, prime mover. So torque mechanical coming from prime mover minus theta, that is the electrical torque converted in armature. Armature induced torque in armature. Converted torque. We already calculated somewhere here, you remember. That is the converted torque. That equation. And then is equal to 0. Torque mechanical is equal to electrical torque. System at an equilibrium point, at a balance. So speed is constant, there is no change in the speed. And then what is happening when you want to increase output power? You apply much more input power in terms of torque, since speed is constant. Then when you apply much more torque, that means you have applied much more input power. That means your machine will convert much more electrical output. Okay, but ladies and gentlemen, when you apply more torque, the rotor leads a little bit. Rotor will be like this. The angle between stator and rotor magnetic field, let me say delta load angle, will increase, but there is a limit. Remember, any magnetic field having 90 degrees displacement between them cannot interact each other. There is no interaction between those two magnetic fields if there is a 90-degree displacement. So it is critical. It is critical. I mean, where is the equation? Equation is not here. Equation was here, or equation is here. Okay, let me write it down here. Converted power, or it is approximately equal to electrical output if array is neglected. If array is neglected, those two are equal, and then 3 times, and let me write it better. That is the armature power, approximately equal to 3 times voltage, current, EF sine delta over XS, and it is approximately equal to electric power when armature resistance is neglected. Okay, here you see, to convert much more electric power, to supply much more electrical output, you should apply much more mechanical input power in terms of torque. So when we increase applied torque, there is an increase in delta. Here's the equation. You have three-phase voltage, you have single-phase winding voltage. That is the synchronous reactance. That is the induced EMF due to rotor field. Here must be some increase, ladies and gentlemen. Someone say that I have increased applied input torque or power. That means there must be some increase here and here. And as you see, voltage is constant coming from network. Excess is constant coming from that device, from the equivalent circuit. EF, you remember EF, 4.44 times maximum flux times frequency times number of turns in armature and armature winding factor. Constant, 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 tata, under very stable network, just like European and so. This is constant. So this guy depends on field current. So it is constant. Under constant field current, of course. If you change field current, that will change. So let me say, in this case, we have kept field current constant. So this is constant. So this is constant. Ta-ta! Under such a condition, when you apply much more input torque, delta will increase, ladies and gentlemen. Delta will increase, and you keep increasing input torque, much more torque here, and then there is an increase in delta. There is an increase in delta. It's up to 90 degrees or pi over 2 radians. When you reach that limit, machine go under out of stability. If it is generator operation, we call pull out point. That is the pull out point. Pull out point. After that point reached, machine speed will be, mechanical speed will be over, you can reach double synchronous speed. And it is dangerous. It is dangerous because those machines are very heavy, large machines. Due to centrifugal forces, mechanical parts would be damaged due to centrifugal forces. So speed must be kept under control. There must be some properly designed braking system. Must be slow down the machine. If you reach such a point, which is minus pi over 2 radians in motor operation region, there will be no push or pull in between those two magnetic fields. Now in motor operation, delta will be lagging, rotor will be in such a position, rotor lags, delta is negative in motor operation, you know, you remember from phasor diagrams. Delta will be positive in generator operation. That is leading, called as leading delta, and that is lagging delta, geri kalan. And then when you apply much more mechanical load to the rotor, delta will decrease down to somewhere here. When you increase load, delta will go down to here and finally here. When you reach minus pi over 2 radians, the relation between rotor and magnetic field will be broken and machine go under out of stability, and rotor speed rotor speed, let me say rotor speed, go down to 0. Here rotor speed go up to double ns. Approximately, not as a general rule, it must be kept below double ns, in fact. Otherwise it will be dangerous for mechanical parts due to centrifugal forces. Okay, we are talk about power balance. We have interpreted stable operating region, why delta will increase. We have discussed as a system point of view. As a system point of view, let's say here's a synchronous generator, here's the electrical output, here's mechanical output, mechanical input, input. If mechanical input is controlled by applied torque, since Ws is constant under constant frequency, so mechanical power can be only adjusted by changing torque. Inside the machine, when you increase applied torque, delta will increase up to pi over 2 radians. Must be less than pi over 2 and 0 in generator mode. When you increase delta torque, there is a delta increase. Applied torque will be resulting increased delta, and delta must be less than 90 degrees and over 0 degrees in generator operation. In motor operation, delta is negative, you know, and it must be larger than minus 90 and must be less than 0 in motor operation. And here you remember minus 90 and plus 90, those regions will be unstable regions. Unstable regions. Okay. Shall I give a break? 5 or 10 minutes? Okay. I give a break here for 10 minutes. Okay, again, come back to efficiency equation. I have just remembered something. Here's the efficiency equation. Generally, those kind of mechanical losses are depend on speed. So, since speed is constant, that guy is constant. Again, frequency is constant, and EMF will change, of course. There's a some change in core losses, and then armature resistance Ra negligibly small, and RF also negligibly small, and sometimes we use superconducting generators. Those are very little, so we can assume that losses will be constant approximately. So you remember from transformers theory. In transformers theory, efficiency with respect to a loading ratio, here is I1 over I rated, which is 100% loaded. That is unity, let me say 0.5, half percent loaded, that is alpha. And then you remember in transformer I say here's alpha star having maximum efficiency. Yes, efficiency will be something like that, will be like that, but efficiency is generally, yes, here it has a maximum value at a point of alpha star, and then there is a slight change, and then it gets smaller. Here is overloaded case. We generally not operate machine under overloaded cases. It is only can be operated for a limited time, otherwise there will be some excess heating, and that is the maximum efficiency. Synchronous machines are very efficient systems, but you know that all the systems in the nature will act similarly, will have maximum efficiency at a certain point, and then there will be efficiency 0 when there is no action on the output. That curves will be similar, but the tendency, slope, or some behavior will be different. But in synchronous machine it is generally smooth. Characteristic is a little bit smooth here. So many times in close to rated operated region, somewhere here, assumed as constant. Here will be, for example, here is 0.97, and then here would be 0.95. So in this region it is assumed as constant. There is not much change in that region close to rated power. Okay, that was something additional about the efficiency problem. And then today we continue on how to find out equivalence circuit parameters. In equivalence circuit, you know, there is EF, dependent voltage source, there is XS in terms of XA and X sigma, leakage reactance, and armature resistance. How can we find out or calculate those items? In fact, we make some calculations in design case. If we are designer, we try to estimate what it would be in the beginning. We try to calculate, estimate the result, final result, what it would be. But after manufacturing process, we generally conduct some experiments to define what those parameters are. One of the experiment is open circuit characteristic. Sometimes we say open circuit test, open circuit test. Sometimes we say no load no load test, or again characteristic. No load characteristic. What does it mean? In fact, earlier in the beginning of these slides, it was somewhere here, I think. Let me find it. I remember. Yes, this guy. In fact, we are aware of these relation. In the beginning of EMF section, EMF is a function of field, as you see, and speed or frequency. If we conduct such an experiment under constant speed, if we measure EF with respect to field current, if we observe this, there is such a relation. In reality, let me make it more clear. Here's a little curve, and then it goes linear, and then it saturates. That is the relation of field current and flux. And that magnetic flux here will result in some EMF under constant speed. That's it. Ladies and gentlemen, that is called as open circuit characteristic of the machine. Today is our topic is discussing open circuit tests. Let me find, I just remember you. Now we are conducting some experiments to measure equivalent circuit parameter. In the generator model, we conduct some generator tests. In fact, it is machine. The parameters are the same, but we conduct some tests. First one is the no load test or open circuit test. Then we will conduct short circuit test. In the open circuit test, let me draw the connection diagram. Open circuit test of synchronous generator. In fact, that topic is can be found here on Turkish pages. It is on the page 106, generator characteristics. As a first characteristic, here is the no load characteristic. It is given here. To conduct no load characteristic or open circuit test, no load test or characteristic. To conduct such a test, first of all, we have a synchronous generator having three phase, let's say star connected. Here are armature terminals U, V, W, and then here's the mechanical shaft, and here's a prime mover. Let me say that is a diesel engine, for example. Prime mover. Here are torque and angular speed of the shaft. Angular speed of the shaft must be kept constant at the speed of synchronous speed. Mechanical side must be kept at the speed of synchronous speed constant. Okay, that is must during the test. And then here are electrical outputs, but no load. So there is no line current. Houston, here is no line current. I1 line is 0. Okay, there is no need to install ammeter here because it is 0. Okay, let me install a voltmeter. There is a symmetry between the phases, so there is no need to install one or more two. One is enough here given. That is a general connection diagram to conduct multiple tests. For example, terminal characteristic, compensation characteristic, we will talk later, and then no load test. All those tests can be conducted by having such a setup. Okay. Now, initial conditions. Initial conditions. There is no current. I1 load 0. No load. That means there is no current inside the stator coil, and then speed is constant. Rotor speed is kept constant at its synchronous value. Constant. Kept constant. Those are the initial setup, initial parameters, and then during the experiment conduct or observe output voltage with respect to let me say another function, with respect to field current, which is one of the control parameter here. Control parameter, field current. How can I control it? Okay, let me substitute a field circuit rheostat, and then here is a constant voltage source VF field plus and minus. By changing rheostat given here, we can easily adjust field current, and then observe field current line to line voltage here. This voltmeter measures line to line voltage. Now, gentlemen, but open circuit test deal with only V1. Beep beep. Under no load test. Beep beep. Take care. Here is the equivalent circuit. Here is synchronous reactance. Here is resistance. And here is one phase. Here are one phase terminals. Between those two terminals, you can measure V1. Ta-ta! Houston. UVW. There is no X. You cannot directly measure that voltage. Houston. V1 is equal to V1 line over root 3 if system is connected star. Here is star connection, so voltmeter measures line to line voltage between phases, and then you can easily calculate single phase or winding voltage by simply dividing line to line voltage by square root of 3. And then Houston, since there is no current, voltage change across those elements will be 0. Since I1 is 0, here is I1 is 0, no current yet, because open circuit, there is no load or no load test. So Houston, what you see here is Kirchhoff's voltage law. induced EMF will be equal to summation of voltages around the loop, which is equal to blah 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 blah. That is the equation defining generator operation. And then, since current is 0, EF is equal to V1. Here you see. Under no load. So I want to say V1 0. Did it? No load case. No load case. V1 0 is equal to EF. Aha. Remember, sometime I said that is the no load EMF. That's it. No load EMF. That is the no load voltage across the terminal. When there is no load, there is no current, there is no voltage change due to no load current. So, induced EMF can be directly seen across the terminals. Okay, that is the, gentlemen, after having such a small calculation, you can easily find out the relation between excitation current and field EMF or no load voltage. Okay, that relation can be drawn like this: EF, IF, EF, and then start experimenting. Start from zero excitation, increase excitation current. There is an increase in field and EMF, and then after having such a voltage, and then there is saturation. During that experiment, I made no change in the direction of field current. No change in direction of field current. That was the increasing curve. And let me draw another curve, which is decreasing curve. Now, it starts somewhere here. Now, Houston, it gets down to here. It returns in another path. There is hysteresis. The EMF, when there is no field current, is the remanence EMF. Remaining voltage, remanence EMF. Or someone can say residual, but that is better. Residual EMF or remanence. I prefer remanence. Okay. When you are increasing, please make no change in direction. If you make some change in direction, the experiment will be bad. Would be like this. If you are going upward and then go back, it comes back in another path, and then when you decide to increase again, there are some tiny hysteresis loops. So experiment will be data will be bad. So if you are increasing, you should keep the direction. If you are decreasing, you should keep the direction. You will make no change in the direction Okay, that is the no load curve. Now, ladies and gentlemen, you remember that is due to in fact field current versus flux. The relation comes from, or genetics comes from here. That is phi r. You remember from electric machinery course 1. That is the increasing, that is the decreasing curve. That is remanence EMF, flux. And you remember EMF is a function of flux and frequency and some other constants. Here are the two parameters defining EMF. Rest of the parameters, let me assign. Those parameters are coming from manufacturing process. After manufacturing the machine, you cannot change the number of turns, the conductors. You cannot change the design. Those are coming from the design. But that parameter can be changed by field current. That parameter can be changed by speed of rotor. But if you operate machine at a constant frequency network, you remember rotor speed is constant. It's at its synchronous value due to 60 F over Poppert number due to constant frequency. Now, that is the no load curve.